Good evening, everyone. Thank you so much for taking the time out of your busy schedules to attend this presentation. Yeah, it won't be too long, and it's just going to be a quick introduction to AI in medicine, as we've mentioned. Again, this topic actually, there's a course at McGill dedicated to this exact topic. I highly recommend it if you're at McGill. I'm actually currently enrolled in that course, and I really am enjoying it so far. So my name is Sharif. I'm a first-year master's student in experimental surgery with specialization in surgical innovation. And I'm working with Recai and Sommer right now in the NeuroSim lab on the EEG simulation project. Yeah, so let's get started then, I think. Just a quick overview for today. So we'll start off with some broad definitions. We'll talk about the significance of AI in medicine, some of the history behind it. We'll talk about specifically machine learning. And then we'll talk about some of the applications of machine learning in medicine. And then we'll focus in on the NeuroSim's work here. We'll talk about some machine learning models, some obstacles to AI in medicine, and then just some frequently answered questions. And as Dr. Del Maestro said, you can ask questions at any time. Please feel free to interrupt, but I'll also be addressing questions at that. So broad overview of AI. AI is actually just simply intelligence demonstrated by machines. It's very, very general. And you can see that it encompasses many different subdisciplines. So for example, NLP, which is natural language processing. So how do you understand semantics given just a bunch of text data? Robotics, so like robotic assisted surgery, for instance, autonomous vehicles like Tesla, for instance, vision, so computer, how does a computer see the world? How does it understand the world? And then machine learning, which is actually a subspecialty of AI, and it's the use of statistical algorithms, to allow the computer to learn patterns, right? And a common way of doing this is using a stochastic approach like simple neural network, where you just have data getting inputted and then having some transformations done onto it, and eventually getting an output that is a classification. For example, you'd be able to classify whether an X-ray is diseased or not, for instance. Another more deep version of machine learning is deep learning, where you're just essentially adding layers onto the architecture. And honestly, the definition between machine and deep learning is pretty ambiguous. There's no clear difference between them, but generally speaking, deep learning is much more layers, and it also involves the bypassing of this very manual process of manual feature extraction, because it can extract its own features. So you can just feed it in raw data as opposed to cleaning up the data, and like you still have to clean it up to some extent, but it's not nearly as much. And so it's a lot more powerful, and it really came to prominence in recent years, and that's why AI has been super hyped lately, let's say. So here's how those three different topics fit in together. So you can see that AI is the broad overview sort of picture, and then machine learning is a subtype, and then deep learning is a subtype. Data science is that whole discipline that looks at all of those things, but also combines statistics, for instance, and linear algebra and much more encompassing things. Here's how they've fared over different amounts of data. So you can see that the more data that you have, the more powerful that certain techniques become over others. Like deep learning, for instance, thrives on a ton of data. So if you have a lot of data available, that would be the go-to technique. And traditional machine learning would not perform as well there. So why are we covering this? What's the significance of this? And for all the medical students and doctors here, it's very important that we familiarize ourselves with this, because it's gaining huge traction in recent years. And you can see that, in recent years, knowledge, medical knowledge has grown exponentially, and it's so difficult to keep up with all that knowledge base. And so AI would allow you to reference that knowledge and apply it appropriately at a moment's notice, which is great. And it also allows you to have, in fact, more patient contact than before, because it allows you to complement your operation, for example, with machine performance, or complement your patient visits with, let's say, a scribe, so you don't have to write down notes yourself. So it saves you time that could be spent to interact with the patient more. It improves your decision-making capacity, and we'll see various examples of that. And because there's an unmet clinical need in recent years, you can see that there isn't enough, let's say, physicians for all the patients that we have. There are a lot of tasks that could be automated that are just being done by AI nowadays, although you still usually get some sort of checking over by a physician. And you can see that these industries are rising to, billion-dollar industries. So robot-assisted surgery being the big one right now, but also a lot of the other subspecialties are using AI. Some broad history. We'll talk about early times and up until the modern day. So the early days of AI, it was just very simple. There's just this philosophy, what is thought? What is intelligence? How do we make a computer mimic that? And then there's this concept of the Turing test. So, how can we allow a computer to fool a human into believing that it's a human, right? The Turing test was made by Alan Turing in the 1960s, 1950s-ish. And he put forth this test that if a computer is able to pass this, then they've achieved intelligence. So this is sort of like a benchmark for how can we grade a computer as being actually intelligent or not. So you would have, let's say, a chat where the computer is chatting with the human, and then you would have another human chatting with a human, and the human would have to discern whether they're chatting with a computer or not. And there's in the modern day, there are a lot of chatbots that could actually beat this Turing test. So it's actually pretty controversial nowadays, because nowadays it's not believed to be the best metric for evaluating intelligence, although classically this was like the go-to metric. Okay, so right after the early days of general thought about AI, we get the symbolic era, where people started making up rule-based systems, expert systems, where you have just basically questions that you can ask that are hard-coded that would allow you to arrive at a particular decision. So you can go through a list of codes, like let's say 100 different rules, and you start, is this living, and then you go on, is this male or female, is this older than 20 years old or less, etc., etc., and then you can arrive at a decision for a diagnosis, for example. So it's largely tree-based algorithms. Then you get the modern era, which really started in the 1990s, where you got a lot of movement away from the rule-based systems and into stochastic, statistical systems. The most well-known of them is the neural network that has been developed, the ANN, artificial neural network, where you just feed in data, it computes some black box function on it, let's say, and then it gives you an output. And that was the powerful change that made AI huge nowadays. Now, when we talk about AI, we don't want to hype it up too much, because that has occurred in the past, and that has resulted in huge issues for the field. Because, for instance, you would see that it rises up a lot, it gets a lot of funding, a lot of scientists go into this, and then you get an AI winter because they realize that the hype that it has gotten wasn't proportional to the success that they could achieve with it, but just because computer systems weren't powerful enough, or there wasn't enough data at hand, etc. And so you go into a winter, and people in AI suffer for a few years because no one is funding them and no one is paying attention to it. And so that has happened already a few times. And right now you can see that we're about to, it looks like we might go into the third one. So I just want to caution against that. So don't leave away with this idea that AI is too amazing. It is amazing, but we have to be careful not to hype it up too much. So some parallel technologies that have driven the AI field: big data analytics, and big compute are the big three. So big data, now the prevalence of a lot of data in one place has really driven this, because as we said before, deep learning architectures require a ton of data, and that's really what's driving the field right now. And we get biosensors and EMRs that are allowing us to have a lot of available data. Then we have big data analytics, which are just techniques for handling big data, and how do you, for example, perform a function at the same time on many different data sources? How do you perform the computational metrics that you need for AI? Because AI at the end of the day is just statistical techniques applied to data. So how are you able to perform that on terabytes of data at once? So within AI, we said that machine learning is really huge, and it's actually what I'm going to focus on mostly for this presentation, just because within AI in medicine, this is what I would say is the most important subfield, machine learning and deep learning, as opposed to natural language processing and other subfields within AI. So within machine learning, you got the three types that we mentioned earlier: supervised, unsupervised, and reinforcement learning. And you already got a sneak peek of this, but just to revise, supervised learning is when you essentially have data that's labeled, and because it's labeled, you show the algorithm some part of that data, and then you train it to predict the other part. So, for example, here's how some data might look like, just so that we don't abstractify things too much. Let's make it concrete. So let's say you have a patient, you have various metrics for that patient, a lot of variables, and then you have a label. Let's say this patient number one is, 0 for healthy or 1 for unhealthy. You would turn this into a matrix, normalize z-score, etc., and then you'd feed it into a model. First you'd also divide it up into training and testing. Usually an 80-20 split between the two is good. And then you feed it into a model that looks at this and tries to predict these labels based on this data. Okay? So that's supervised machine learning. For unsupervised machine learning, you don't actually have these labels. What you do instead is feed this data, and it learns to cluster the data. So here's an example. You feed it a lot of data, and it builds, without knowing labels, it builds a certain number of clusters, let's say. And then if you were to show it another example, then it would just correlate that example with the one that it is most similar to. So here you can see a principal component analysis, which is essentially a way to display multi-dimensional data in, let's say, 2 dimensions in this case, where you have proximal tibia X-ray data clustered into 9 or 10 clusters. And so if I were to take another X-ray and quantitate all of the data there, I could arrive at a certain cluster here. And one of these clusters could, for example, be associated with a certain prognosis, while another one is associated with a different one. Okay, so that's unsupervised. This one is reinforcement learning. This is a third type. It's not talked about as much because it's not really applied in medicine as often, although it's picking up a lot of traction lately. So essentially you have punishment and reward for certain actions. It's really common in autonomous vehicles, for example, where, a humorous example would be you get a simulation of a car driving, and that car will drive randomly, okay, and you will give it reward for every meter that it takes, let's say, and you will punish it if it deviates from a path or something like that. So for example, you could get a simulation of a car driving, and it'll drive and drive and drive, and eventually it'll fall off a cliff, let's say. And then next time, hopefully it'll learn that, it shouldn't fall off that cliff, because then it'll get punished for that. And, after maybe 10,000 iterations, it'll finally learn not to fall off that cliff, and it'll learn how to drive correctly. So a lot of work going into this field right now. But we'll focus on the other two, though. Okay? So now we're going to talk about some applications of AI, specifically with regards to diagnosis prognosis. We'll talk about the smart scribe system, and then we'll go into the case study of our lab. Some application within diagnosis is, for example, pneumonia versus healthy detection. What this group did is they actually, at the beginning of the COVID pandemic, they referenced the literature on pneumonia, and they essentially took a lot of x-rays from pneumonia patients because there wasn't a lot of x-rays available for COVID patients. And so they trained an algorithm on detection of pneumonia versus healthy patients. So it could classify, for example, given an x-ray, whether it's a normal or pneumonic patient. And after that, they trained that model on a few examples of COVID-19 x-rays, and they'll learn to actually discern between normal and COVID-19 x-rays, just because COVID-19 is fairly similar to pneumonia, let's say. And so it learns that pattern. We also have a lot of prognosis survivorship prediction within medicine. So this is a great paper by Jeffrey Dean at Google. And they essentially tried to compare deep learning with traditional machine learning techniques across inpatient mortality prediction at 2 different hospitals in California and Michigan. And so what they did is they compared sensitivity and specificity. So they generated an ROC curve, and they plotted the area underneath the ROC curve across various times in the admission process. And so they were able to get really good high accuracy predictions of inpatient mortality using the deep learning techniques that greatly surpassed the traditional learning techniques in both hospitals. And so you can see that, the closer it was till the time of mortality, obviously the more accurate their prediction was going to be because they had more data at that point to work off of. Smart scribe system. So this is one paper laid out by this group. And essentially, a lot of people are working on this right now just because it's, one, expensive to hire people to transcribe for you all of your techniques. And two, it's natural language processing right now has gotten to the point where it can actually outperform humans in a lot of this work, especially in, let's say, particular vocabulary areas like the doctor's visit. And so you would have, for example, a sort of Alexa-like device that's listening in and then recording the patient visit. So then the doctor doesn't have to spend all that time recording the visit themselves. This is the case study for our lab. So we have, let's take, for example, surgical education as one application of AI potentially. Surgical education has had a lot of issues. You can imagine that it's a very complex procedure, and the tissue that you're dealing with is very fragile. So you can have very dire consequences if you're not careful and if you're not adequately trained. So one, or rather, traditionally, how you would train neurosurgeons is through residency. And so you would, observe the neurosurgeon over time and get to conduct some surgeries yourself. And so you get progressively, as you advance in your training, more and more responsibilities, and eventually you're, let go into the field where you're practicing neurosurgeon. And then really VR and other simulation technologies have transformed this idea, because now we could actually get the neurosurgical resident to do very similar training to what they're going to see in real life, and very realistic training as well. And so you can see that VR technologies have risen up, and actually McGill is one of the leaders in this. And so we have a few papers outlining how VR could be used in neurosurgical education, and I'll explain some of those. This is the platform that we're using. Can everyone hear? So it captures data like velocity, acceleration, etc., how much the patient was bleeding. Okay, so there is one big problem with using that technique. It's great, obviously, that VR is available to help you simulate the surgery. But how do you grade your surgery? How do you know how well that you performed on that surgery, right? So that's where we could use AI to address this issue of quantitation. Um, because there are no hard operative outcomes, right? We don't know exactly what makes a really good surgery from what makes, a less good surgery. So here's one paper that we published in the Journal of Surgical Education that attempts to address this exact issue. So the idea is that we would assume that surgical education, and there's a lot of evidence to support this, that surgical education is proportional to expertise. So let's say a neurosurgeon is more of an expert than a neurosurgical resident, which is more of an expert than a medical student. And so we would use those as broad categories, and we would take the performance metrics and try to correlate them to each of the surgical expertise. And that way we could give you a performance rating after each surgery. And now we're working on also real-time performance ratings. So, at every second of the procedure, let's say, what level are you performing? And that way you have some feedback as you do the surgery. Okay. So here's one example of that, where we tried to classify just senior versus junior. So let's say more senior people, maybe neurosurgeons and senior residents, versus junior residents and medical students. You can see that we achieved a very good sensitivity and specificity here with a total accuracy of 97%. So you can really discern well between them using this NeuroVR system, and that way you can give real time feedback as people are conducting surgery. One of the technologies that has advanced that has driven AI is the widespread availability of data. Healthcare specifically has had a huge boom in this because of the rise of EMRs, so electronic medical records, medical tests being widespread, genetic analysis, and then physiological data recordings through Internet of Things objects, like smartwatches, for instance, and medical images. So let's go through each of those. EMRs, which have been widely adopted now, are a great way of storing all the patient's information in one place, but also are a great way of structuring the patient information, which allows algorithms to then compute results based on the data. So you would feed in, as I showed you earlier, for example, Jeffrey Dean's group literally just fed in the whole electronic medical record into an algorithm by structuring it in a certain way, and they were able to predict ICD. They predicted ICD-9 codes, but you can also predict ICD-10 codes if you wanted. ICD-10, I think, stands for International Classification of Diseases. They're just a bunch of medical codes that uniquely identify every disease. And so with the rise of good data structures like the ICD-10 and good data storage places like EMRs, that has really driven AI in medicine. Also, we also have obviously biomarkers and medical tests that you can record the data. A lot of this data is also recorded in the EMR. And you also have genetic tests. So and even to the point where they're individualized now and like privatized, where 23andMe, for example, Ancestry DNA would allow you to, for like $150, let's say, to take your own DNA test, and you could find out a lot of information about that. But you can imagine genetic tests are huge in terms of data because you have 3 billion base pairs, and each one of those base pairs becomes a data point ultimately. And so that's proportionally huge compared to everything else, actually. This is like the largest source of data. Medical images, let's say like MRI, for instance, or just X-rays, also really big. And they're analyzed in specialized ways. There are whole pipelines that are specialized to medical images for AI. And then Internet of Things like Apple Watch, which is huge. There's recently the Apple Heart Study at Stanford that learned how to diagnose atrial defibrillation based on your pulse. And then this obviously has the advantage of being hugely widespread and available to the consumer market. So you can collect a lot of data and then help people in real time. And as promised, we don't want to hype up AI too much, so I do want to mention some of the obstacles that AI has faced in recent years, and we'll go through each of these. But generally, the prevalence still nowadays of unstructured data, uniquely so actually in medicine compared to other fields, and then data silos, some issues of confidentiality, the issue of interpreting algorithms, and like some ethical dilemmas that can arise, and then the issue of bias. So unstructured data is whenever you have, the simplest way to define it is it's data that's not possible to put in a table adequately, okay? And so this may include something like a doctor's notes. Let's say the way that he transcribes, she transcribes a certain patient visit. And that would not be possible to put in a table, obviously, because it's very, like there's basically an infinite number of ways that they could write it, and there's an infinite number of ways that they could structure it. And so it's very difficult to work with this sort of data, and it's presenting a huge issue in medicine right now. You can imagine that doctors in particular have like are notorious for their bad handwriting, and so they in particular we have issues with in terms of computer vision analysis of their handwriting. There's also this issue of data silos where people just, let's say, keep their data to themselves and they don't put it on open source areas where we could combine data and therefore be able to make better models. Just a personal anecdote for myself. At the beginning of the COVID pandemic, as we saw before, it's very widespread, this idea of diagnosis using X-rays. And I knew that, for example, COVID testing was very difficult to come by, and they were struggling to develop good, accurate tests. And so what I did to try to do my part for this pandemic, I actually gave a call to this hospital, which if everyone remembers, this is actually the hospital that China built in around a week that has 1,000 hospital beds. So I figured they would have a lot of COVID data, right? So I called them, and essentially, like no response. It's so hard to get data from these scientists, just because everyone is obviously in a rush to publish AI algorithms on that data as well, and because of the other issues that I'm going to discuss, such as confidentiality. Because with healthcare data, obviously it's sensitive data. I'm sure a lot of, let's say, insurance companies want their hand on this data. There's just so many nefarious uses for them, and so it's very important that we respect confidentiality. There's actually, like, even if you remove a patient's name and a lot of their characteristics like age, sex, etc., there's actually algorithms that de-identify it. So there's that identify it after de-identification. And so it's very difficult to get this area right just because of that. And so people just take the safe way out and not publish their data at all. There are some attempts to publish data, although they're not as widespread as we would like. One issue is interpretability of the AI models. So they're largely referred to as black boxes. I don't know if anyone's heard of this term. This concept that you put something into it, it does something to it, and then it gives you an output. And you don't know exactly what it's doing to that data to arrive at this output. And so that's a problem, especially in medicine, because for example, the EU actually passed a law that says that if you use an AI model, then you have to be able to interpret that model. You have to be able to tell the patient exactly how that decision was made. And it's very likely that North America is going to legislate accordingly. And so we're developing a lot of these packages that allow you to interpret the models. So this particular interpretation technique is called Shapley, and it's based on some game theory approach to interpretation of models. And essentially, it allows you to pick out exactly what variable that you fed into the model that the model looks into the most, what variable is the most important in arriving at its decision. And so this sort of package is invaluable in the healthcare industry for AI. You also have the rise of dilemmas whenever you use AI. Oh, because mainly of that black box issue. And because AI is such a fast-moving field, that legislation is struggling to catch up, right? And this is an issue with a lot of the cutting-edge fields. And because it could be exploited easily, we need to, like a lot of dilemmas are arising for this. So for example, would you trust a robotic surgeon to operate on you that's operated based on AI? Or would you, again, with the legislation um, with the legislation that says that you have to be able to interpret AI, would you be willing to? One big issue is these deeper neural networks are often the ones that are more difficult to interpret. The shallow ones are very easy to interpret, but the deep ones provide you with the higher accuracy. So are you willing to sacrifice accuracy for interpretability? Is that ethical? Would you risk getting misdiagnosed at the benefit of knowing exactly how you were misdiagnosed? It's definitely a dilemma. And then another issue is bias. A lot of AI models are biased. So they, for example, the go-to case for this is, do I have this somewhere? I don't. Oh yeah, no, the asthma patient. So there was this one notorious model that learned how to diagnose pneumonia based on EHR. And it learned based on the pattern that it was fed, it learned that asthma patients just are very low risk of pneumonia. And we know clinically that that's not correct and that something went wrong in the learning process there. So they discovered that when they were training this when they were training this model, that the hospital policy was always to send asthma patients to intensive care. So that in that way, asthma patients were almost always disregarded from the required further care label. This was a supervised machine learning model. And so the model learned that if you're an asthma patient, you don't require further care. And so that's a big incorrect error, and it's completely biased. And so we have to be careful for something like this because obviously, if you depend on this sort of model in your diagnosis, then you're going to be harming patients, and we don't want that. Um, some quick FAQs for AI in medicine. So will AI replace clinicians? Like this is a very common question you get all the time. The quick answer is no. We're not trying to replace physicians here or anything like that. We're trying to supplement their practice. We're trying to give them more patient contact, trying to make it easier to, or like really, we're trying to make the practice of medicine more humane. And this is a great book that I highly recommend by Dr. Eric Topol in the States. And he's really involved in this field. He's in the University of California at San Francisco, UCSF, and this is one of the hubs for AI in medicine. And he really lays out a framework for how he envisions AI and medicine, supplementing. And it's called Deep Medicine. Highly recommend it. Okay, and how do you get started in AI? Let's say you want to get started and you want to learn, and there is essentially no defined framework, but I can give you some guidelines on how to get started. Obviously, it depends on your background and depends on how much you already know about it, etc. So first thing I would recommend is just understand the fundamentals of AI and just understanding how AI works. You can do courses on Coursera. Deep Learning AI it has a course on Coursera, but it also has its own courses. I would highly recommend. You can also learn ML specifically, zero to hero. So literally nothing, not even linear algebra. And they will teach you everything you need for the fundamentals. There's a YouTube channel, TensorFlow, you can look into. You also generally need to learn how to code. There is this move nowadays for codeless, let's say codeless architectures. You don't need to know how to code to make them. You can just map things out in sort of like an Excel sort of mapper, let's say. But nowadays, mostly you still do need to code, unfortunately. So there is that steep curve at the beginning if you don't know how. And the most common languages are MATLAB and Python, although JavaScript is also picking up in recent years. But I would personally recommend Python just because even though it's great for data science and there's so many resources available for it, it's also what's called a Turing complete language. So on top of learning how to do data science and how to do ML and AI, you could also generalize that and code basically whatever you want in that language. So it's very, very versatile. And TensorFlow itself is actually a Google-based framework for deep learning that just handles tensors for you, which is the, I guess, the generalized form of matrices. And so it allows you to make very complex models. And when you combine it with this, let's say, abstraction known as Keras that sits on top of TensorFlow, you can actually generate a deep learning model with less than 10 lines of code. So it's become very democratized nowadays, and anyone can get involved in this. So here's our lab, or just some of the members of our lab, and that's all. Thanks a lot. So I could be taking any questions.